The good news is we're all singing from the same song sheet here in terms of sorts of problems and issues that need to be addressed. So I'm going to be looking more from the fluid side, and fluid compositions reflect a number of things, which have already been touched on by the previous two talks. But there's fluid flow paths, both near field and far field effects, mineral dissolution and precipitation, equilibration temperature, chemical geothermometers, chemical structure of reservoirs. Joe nicely illustrated two examples, Raft River and Thermo, where chemistry varies just within the resource. Chemistry should be reflecting the extent of the resource, and I mean in terms of temperature distribution, their baseline versus production-induced effects. And a key point here is that geochemistry is important not only from an exploration point of view, but also during development and production. The geochemist is also analyzing fluid components for all the other things that are in the fluid besides just things that are going to degrade the resource. Joe made reference to salt and sea production of other constituents, some metals, lithium, but there's other things too, like helium. Maybe some of you know this, that helium is an important commodity that's becoming increasingly scarce. When you drill into the subsurface, we're always finding out new things, and we should be surveying and characterizing the fluids as fully as possible to see what's in there. You can have a long production history and realize after 10 years or 20 years that you've been losing a valuable commodity just by letting it escape at the surface and haven't been capturing it. So questions that I think are important. These are not all new questions. They are ones that have been part of the geothermal community for a long time. You can put where or what in front of either of these. So where is the resource? What are the fluid pathways inside and outside of the reservoir that might be affecting the fluid compositions and the extraction of heat? What's the nature and the scale of compositional variability? How do host rocks and minerals influence that compositional variability? And we can think of in the sedimentary environment both the siliciclastic and also carbonate units, as Joe mentioned. We also have to be thinking, what's the state and the extent and time span of fluid-mineral equilibria? The experimental world gives us good insights as to what's going on over short time scales and at very small scales, which is really critical. But we're going to have to build that up to path lengths and or dimensions in both space and time that are kilometer plus and decadal plus in terms of understanding processes. We also want to know what the sources of aqueous and gaseous species are. Don't expect them to be coming from the same places. They'll be coming from different places. And Joe nicely illustrated some of the possibilities. Because drilling's expensive, we want to be extracting information from proxy environments. So the oil and gas industry's got a lot of experience with injecting heat, steam floods, water floods. What's the information that we can extract from that, albeit short time scale of water rock interaction, what stuff comes out. There's experience with oil shale and also conventional geothermal, and they've been touched on in this conference. And also, I would say there's scope for even looking at paleogeothermal systems such as ore deposits, Carlin gold deposits, and Mississippi Valley type lead zinc deposits are both hosted in siliciclastic or carbonate units. These are likely to be, at some scale, a paleo proxy for the sorts of environments we're looking at. Keep in mind that geothermal energy occurs in a diversity of geothermal or geological environments. We have a lot of experience in dealing with these flowing environments where we have some sort of deep heat source and fluids are moving through columns of rock with very strong buoyancy effects. In the sedimentary basin environment, fluids may be in residence for very long periods of time. We sort of think of them as being largely closed or with a lot of storage effects, but they certainly could have dynamic components to them, and there's evidence from, I know of just in the literature of the Illinois and Michigan basins where, just like Joe described for Raft River, there's evidence for glacial waters to be infiltrating into basin stratus. So, and also in the deeper parts, hotter parts of sedimentary basins, we can expect decarbonation reactions to be taking place, which may be liberating CO2, depending on how it's coming into it. So that may be bleeding into the lower part of a reservoir. Well, I don't. This is. We can take this for granted. We know these wells are expensive. We want to preserve them for a long period of time. The thing about geothermal energy, point not lost on this audience, though, is that it's a long-term investment. There's a long-term benefit. It's arguably transgenerational. So it's good that there's some young people in the audience here to be thinking about what they might learn, because it may take 20, 30 years before this stuff actually takes any commercial traction. Joe said that everything occurs in the Salton Sea hypersaline brines. Good thing is that chemically we can just about analyze all those things now, and the advances in geochemical techniques over the last 20 years now allows us to get down to parts per billion level, even parts per trillion level, with a lot of trace components. But these are the constituents that are normally analyzed in the geothermal context. I won't go through them all, but their application is either as a tracer, so we can understand where fluids are coming from or how they're moving through a rock mass, or they're an indicator, which is providing some indication or interpretation of, say, a state of equilibria, which is reflecting temperature. There are other issues as well, engineering and environmental, which also demand chemical characterization. Within sedimentary basins, we can think about the sort of dimensions of these resources. These are not, they're probably not as dynamic in terms of state of change of transient heat pulses as volcanic or say Great Basin type resources, but we still need to be thinking about the scale of transient effects. We might assume initially that there are broad physical gradients so that temperature distribution is relatively homogeneous, and certainly there's no expectation of a pressure drop because these are laterally extensive rather than vertically rising columns of water. Nonetheless, in terms of thinking about what sorts of reservoir processes are going to be controlling fluid chemistry, we know that there's going to be a rock-dominated environment where minerals surround pore fluids, and this is a place where fluid-mineral equilibria is going to be established. It's where chemical geothermometers or the underpinnings of chemical geothermometers are developed. And once the fluid moves into an open space, and the fluid can move, if there's a pressure gradient, relatively fast, and there's greater likelihood that physical processes, some cooling, mixing, or phase separation will become more important in terms of changes in fluid chemistry. So just a different context of where fluid chemistry will be important. We can think about it in an exploration phase. Of course, you may be wondering, deep sedimentary basin, where are we going to get our fluid? Well, one place you might be looking is from an oil and gas well. You might be looking at whatever water chemistry data are available. We should also be thinking just in a way that many oil and gas reservoirs were discovered, that there were oil seeps. So there may be springs coming up to the surface, providing indications of this deep fluid, and albeit modified, by cooling or water rock interaction, there may be constituents that give us clues about the possibility of this deeper geothermal resource. And I'll try and touch that on an example at the end. Once you drill a first well, you have the opportunity of sampling fluids. It's critical that wells permit good fluid sampling, and probably one of the issues is actually resolving the scale at which you are sampling fluid, because as many of you appreciate that in a well, you're going to mix fluids from different horizons if they're all allowed to produce simultaneously. And who knows where the dominant production will come from. Won't know that until the well surveys are done. In high temperature geothermal systems, it's common that there's only 1, 2, or 3 major feed points in a geothermal well, and these feed points may be only of centimeter scale. Consider that as you advance the exploration phase, you're going to be able to get more spatially distributed data points. You're going to be able to improve your understanding of what's controlling fluid chemistry, and just keep in mind that reservoirs may be leaky either through the tops or the bottoms, allowing ingress of fluids from either sides of the reservoir. And then what goes on during production. Obviously, in the rickalysis scenario, we're going to be looking at injection and production. I expect that these are going to be moving around through a reservoir over time. So as resources degraded. So there are issues both within the time frame of injection production, but also possibly over a much longer time scale if you abandon parts of the reservoir, that you might be able to come back to it if heat recovery is possible. And so maybe not in 10 years, but perhaps in 50 years, and you might be thinking about what I might do in that injected fluid that will help preserve the permeability characteristics that make this a sustainable reservoir for a very long period of time. Joe mentioned that there's a wide range of fluid compositions in geothermal systems. One of the things that I think is really critical, and Joe touched on this as well, is carbonate equilibria. We know that, and so by carbonate equilibria, I mean not only reaction with calcite or other carbonate minerals, but CO2 and CO2 concentration, and also pH. So that's probably one of the most sensitive reactions that we have to think about over the scale of the reservoir and also locally in terms of what might be scaling in wells. Got a diversity of rocks and minerals in these environments, potential sources of reactive components. We also, if we look at lessons learned from oil and gas industry, and I'm certainly a novice to these, but we know that gas production can have a thermogenic or a microbial origin, and that even during production of oil and gas reservoirs, you can get gas souring through sulfate reduction. And this leads to alkalinity changes which affect calcite solubility. We also, it's unlikely that, well, I don't know what the likelihood of phase separation is going to be in these environments. It depends on the pressure gradients. Mixing is going to certainly be important. And I would say, and I'm going to touch on this briefly too, that there's a role for developing chemical geothermometers. We're at a very early stage of having anything useful for the benefit of sedimentary basin resource development. So I want to show you some water chemistry that is available from the literature. These are from oil and gas wells in Nevada, California, Texas, and then the thermal water, which Joe referred to, and then a geothermal field in New Zealand called Nafa, which is hosted in siliciclastic rocks entirely. And just give you a sense of compositional variability, just looking over there at the chloride concentrations. So we go from relative dilute to somewhat saline solutions. Sulfate and bicarbonate are variable, and down here at NAFA you can see that there's very high bicarbonate. This is due to the very high CO2 concentrations that are present in that fluid. All of these waters, at least in the laboratory, are a relatively neutral pH, and that's good news. So you can take these data and you can process them in a geochemical context, and I'll just show you a couple of results of some of that processing. A simplistic graph of taking temperature reported for the waters and that they were collected at versus, say, silica concentration. Quartz silica solubility relationships have been used for a long time as a chemical geothermometer. You can see that there's coincidence between where these data plot and silica polymorphs. Here's the quartz solubility curve. Here's the chalcedony solubility curve. Here's the cristobalite solubility curve. And you can see that there's a clustering. I won't say it's strong, but there's a good enough clustering, even when we go to hot temperatures, that shows that these minerals are likely to be the strongest controls on silica concentration. And these are probably the most promising basic geothermometers. At the very least, silica will give you a minimum temperature. One caveat about chemical geothermometers is that I mentioned this the other day in the short course. They're an interpretation. So for those of you who didn't hear that, they're not a number that you can process in a statistical kind of environment. Standard deviations on averages of chemical geothermometer results isn't going to be a very useful number. All of these waters are calcite saturated, and many of them are dolomite saturated too, based on an assessment of full fluid mineral equilibria. We can look at some of the other relationships, sodium-potassium ratios, which are commonly used for chemical geothermometry. The basis for that is equilibrium with potassium and sodium feldspars. There's only one water sample that plots at equilibrium. That's the sample from NAFA in New Zealand. That's 220 degrees Celsius. It's right on the line. But these other cooler basinal waters are plotting away from that curve. They've got some scatter to them. I don't know what the potential, well, the preliminary results would suggest that there's not much hope of developing a geothermometer on the basis of sodium-potassium ratios, but I would say a lot more work needs to be done to resolve not just the chemistry, but what's the reliability of the temperature measurements here on which I'm used to plot on a graph. And I really don't know where the temperature data are coming from in the papers that are reporting these data. So we need to drill deeper into where that temperature data come from. There are other empirical geothermometers that have been developed based on lithium. There's a magnesium lithium and a sodium lithium chemical geothermometer. These have no thermodynamic underpinning. They were just basically, let's take a pile of data and do regression analyses on them and see what pairs of elements or constituents form some sort of temperature relationship. Sodium, so here you see the sodium lithium geothermometer. This is fully active shard, and some of the data cluster around the line, but there's NAFA way down there, and so there may be some issues of reliability. So just summing up, silica appears to be the most reliable. Controls on cation ratios inadequately understood. There's some issues about reliability of temperature, and maybe, certainly the analytical data. I have no reason to criticize the analytical data, but I just have no control on it because it's published data. We also need to be careful because in a geothermal environment, when we're worrying about, say, calcite dissolution or precipitation, in order to compute that equilibrium, we really need CO2 data. And we need to couple that with pH, and we need the bicarbonate simultaneously. So we need these data to understand if there's any risks or benefits by manipulating CO2 through the reservoir. So I think these data are a little bit more difficult to acquire in an oil and gas environment, but I'd be happy to be corrected, and I'd certainly like to see as much of that as possible. Some preliminary reaction path modeling suggests that in the short term, and under the sort of scenario that both Rick and Joe described, there's going to be no scaling problems in the production wells. And I'll just show you one of those reaction path models here. This is for thermo. This is for the hottest water at thermo. And what you see here is I've just adjusted the pressure. Well, this is just the saturation pressure declining as the temperature cools from 175 down to 50 degrees C. There's some pH change that's modest. Of course, the water is saturated in quartz, so as it cools, you'd expect it to precipitate, but probably with the benefit of kinetic impedance, most of the silica will stay in solution and just be allowed to run through the fluid can be run through the heat exchanger without any problems. Down here on the bottom axis, this is the saturation index. As long as these values go below 0. So you can see that all the carbonate, all these minerals are becoming undersaturated as you cool. That's what you expect because of the reverse solubility. But in terms of the questions about what happens on injection, of course these things are all going to heat up. And if it's a closed system, they'll all come back close to saturation. So the thing about injection is you're allowed to add some other chemical constituents that might minimize any deposition once you're injecting this fluid back into the reservoir. I can't emphasize the importance of calcite and carbonate equilibria. Joe mentioned the reverse solubility. We don't really expect temperature to be a big effect in terms of calcite deposition. The bigger effect is the role with CO2. This is a chemical reaction that shows that calcite and CO2 are on the same side of the reaction. So this is high CO2 and calcite deposition, same side. The reactions that Joe described, CO2 is opposite from calcite. And it takes a little while to appreciate some of the subtleties of carbonate equilibria, but CO2 can react with minerals that contain calcium, and so high CO2 can cause calcite deposition in the kind of environment that Joe was talking about. But if we have open space and we're just in a fluid-dominated environment, no. High CO2 will cause calcite to dissolve into calcium and bicarbonate. So if we inject CO2, we can dissolve calcite. And of course, if we remove CO2, say due to phase separation, we'll precipitate calcite. Well, in terms of reservoir porosity and permeability, this could be really important. And here are just two thin sections that Gene Klein gave me. These are from a Carlin gold deposit. These are in northeastern Nevada. They contain huge amounts of gold. The thin section on the left shows a mudstone with calcite veins. And over on the right, the blue represents where the calcite's been removed. This is over a distance of 100 meters, and all the permeability that allowed for these ore deposits to form was generated by dissolution of calcite. So there is the possibility that CO2, and that permeability still exists today. So that's not a modern process, that's a paleo process. So that could be quite important in terms of understanding poral perm distribution in a modern reservoir. This is a map that Rick Alice published last year, I think. He shows, just in the Great Basin, the extent of the carbonate rocks that could possibly form geothermal reservoirs. Over here is Biowaway and Tuscarora geothermal fields. There's another one that's blind, that's in a mine called Midas up here. These are just inside the limit of this distribution of limestone and carbonates. These are intermediate temperature geothermal systems. They've had long-lived production, and they produce bicarbonate waters. Tuscarora has limestones in the drilled parts of the reservoir, but at Biawawe, there's only siliciclastics. The only source for that bicarbonate has to be an underlying bicarbonate rock. And while we may have questions about the reliability of some of our chemical geothermometers, the preliminary indications are that they indicate 250 degrees Celsius. So what's the possibility that these geothermal systems are just the leak-off points for a much larger carbonate-hosted geothermal reservoir in the subsurface, and that this temperature is more representative of what the deep resource temperature in that much larger scale geothermal setting might be? We're always thinking about possibility as much as we're thinking about probability and predictability. I'll just finish with this last slide. You can't do chemistry or geochemistry without all the other physical processes and without the geological context. You'll remember that your geochemistry could lead to geochemisery if you don't pay attention to it. And also, if you're not part of the solution, you're part of the precipitant.